Hello, everyone, and welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is Z-transform theorems. There are several important theorems related to the Z-transform. They will help us analyze and design discrete time systems easier. These theorems are time shifting, time reversal, differentiation in the Z domain, and convolution. The first theorem, the time shift theorem, states that given the transform pair x of n and its z transform, with ROC denoted by Rx, the z transform of the time delayed sequence x of n minus n0 is equal to the expression shown here, with ROC equal to Rx. This theorem is used when we want to find the transfer function of a digital filter, or when we are trying to convert a difference equation into a ratio of polynomials in Z or 1 over Z. The transfer function is the Z transform of the unit sample response of a digital filter. So again, it's basically a generalization of the frequency response. To prove this theorem, we call the new sequence, the shifted sequence, y of n, and we take its Z transform using the definition of Z transform. Replacing y of n with x of n minus n0 and applying a change of variable calling n minus n0 m, and simplifying the expression by factoring out the constant term z to the power minus n0, notice that the remaining terms is equal to the Z transform of x of n, and this proves the theorem. For a discrete time non-recursive LSI system or an FIR filter, the input-output relation is described by the difference equation shown here. Without loss of generality, we can set n1 equal to 0 and n2 equal to n and get a simpler version of the difference equation. Now, if we take the Z transform of both sides of the difference equation and apply the time-shifting theorem, we get the algebraic equation shown here. Using this equation, we can write the expression for the system transfer function, which is defined as the Z transform of the output sequence over the Z transform of the input sequence. As you can see, the transfer function of a non-recursive system is a polynomial in powers of 1 over Z. Let's look at an example. Let's find the transfer function of a moving average filter described by the difference equation shown here. Taking the Z transform of the difference equation and applying the time shift theorem, we get the algebraic equation shown here. Finally, factoring out the term x of z on the right-hand side, we can solve for the transfer function, the ratio of y of z over x of z. Now, IIR filters are modeled by an nth-order linear constant coefficient difference equation of the form shown here. Taking this difference equation into the Z transform domain and applying the shift theorem, we get an algebraic equation, which we can solve for the transfer function h of z, the ratio of y of z over x of z. As we obtained here, the system transfer function of an LSI system, a linear shift invariant system, is always a rational function. As an example, let's find the system transfer function of the IIR filter described by the difference equation shown here. Using the time shift theorem, we can transfer the difference equation into the algebraic equation shown here. Simplifying the equation, we have the system transfer function h of z as the ratio of the Z transform of the output sequence over the Z transform of the input sequence. We can simplify and write the expression in terms of Z. Given the transform pair x of n and x of z, with ROC denoted by Rx, the Z transform of a time reverse sequence x of minus n is x of 1 over z, with ROC equal to 1 over Rx. To prove the time reversal theorem, we again call the new sequence y of n and we take its Z transform using the definition of Z transform. We apply a change of variable we call minus nm and simplify the expression. What we are left with is the z transform of x of n at 1 over z, and this completes the proof. Let's see an example. Given the transform pair x of n as 2 to the power n un and its z transform with the ROC shown here, use the time shift and the time reversal theorem to obtain the z transform of the new sequence shown here, the left-sided exponential sequence y of n. If we rewrite the expression for y of n so that the coefficient minus 2 to the power n is written in terms of exponents minus n, multiply the coefficient and divide by 1/2, we get the expression shown here in terms of minus n minus 1. And this gives us the expression for y of n in terms of x of minus n plus 1. Now, since the new signal y of n is a time-shifted and time-reversed version of the x of n, we can apply the two theorems. Now we can write the z transform of the new sequence y of n in terms of the z transform of the sequence x of n, with the ROC as indicated here. The differentiation in the z-domain theorem states that given a pair of sequence and its z transform with ROC denoted by Rx, then the z transform of the sequence n times x of n is minus z times derivative of x of z with respect to z with ROC equal to Rx. To prove this theorem, we take a look at the derivative of x of z with respect to z. Simplifying the expression and taking the derivative of the term z to the power minus n, we rewrite the expression by factoring out a minus z to the power minus 1. Multiplying both sides of the equation by minus z, we get the expression shown here, which proves the theorem. As an example, given the z transform of the sequence x of n as shown here, let's use the differentiation theorem to find the causal sequence y of n whose z transform is given as indicated here. Following the terms in the differentiation in the z-domain theorem, if we take the derivative of x of z with respect to z and multiply by minus z, you can see that the expression that we get is equal to y of z. And so according to the differentiation theorem, the sequence y of n is equal to n times x of n, or n times u of n. We can use the Wolfram language and take the z transform of nun and verify that the result is correct. The last theorem that we cover in this lesson is the convolution theorem. Given two sequences, x1 and x2 in time domain and their z transforms, with ROCs denoted by Rx1 and Rx2 respectively, the z transform of the convolution of the two sequences in time is equal to the product of the z transforms of the two sequences, with ROC containing the intersection of the two ROCs. We follow the definition of the z transform for the convolution sequence, change the order of the summation, and apply a change of variable called n minus k m, and simplifying the expression by breaking down the exponential term and factoring out z to the power minus k. Note that the terms in the parentheses is equal to the z transform of the sequence x2 of n, and the remaining terms are the z transform of the sequence x1 of n. And so this is equal to the product of the two z transforms, with the RC including the intersection of the regions of convergence for x1 and x2. Let's use the convolution theorem that we just discussed to find the convolution of the two sequences h of n and x of n as given here. Using the Wolfram language, we need to take the z transform of each of the two signals, multiply them, and take the inverse z transform of the result. Or without using the Wolfram language, we first find the z transform of h of n and x of n. We multiply the two z transforms, simplify the results, and take the inverse Z transform of each of the terms in the product of the two Z transforms. In this lesson, we looked at some of the important Z transform theorems: time shifting, time reversal, differentiation in the Z domain, and convolution theorem. We defined the system transfer function, and we looked at several examples of using the time shift theorem to find the system transfer function of FIR and IIR filters.